water comprises a small fraction of the total amount of gas in the atmosphere, it plays a crucial role in our day-to-day weather and in our global climate. This is seen most clearly by observing the water cycle in the atmosphere. The water cycle is the cycle of moving and transforming water molecules from liquid to vapor and back again to liquid. We begin with evaporation from oceans and other bodies of water. As this air rises, it condenses to form clouds. The wind in our atmosphere moves these clouds over land, leading eventually to precipitation. As rain and snow accumulate on the ground, they produce water for lakes and streams, while producing runoff back to the ocean. And thus the cycle continues. As runoff returns to the ocean, that produces additional condensation. As wind blows clouds over land, it leads to precipitation, which again returns into runoff. We also expect that the amount of water in our atmosphere plays a very critical role in our major storms that we observe, whether it's through strong thunderstorms or whether it's through the development of very strong monsoon circulations. Furthermore, the absence of water vapor in some regions of the world can lead to droughts, and it can aid in wildfires. Therefore, changes in moisture or humidity are an important part of daily weather. In this video, we will discuss a simple method for monitoring and measuring the amounts of moisture in our atmosphere. Now, the instrument that we will use to investigate the moisture in the atmosphere is known as a sling psychrometer. A psychrometer is any instrument that can be used to directly measure moisture, and it does this by looking at the evaporation of moisture on the thermometer. So the basic construction of a sling psychrometer is going to be based upon the following features. You will need to have a standard thermometer seen here, and this is going to be what we call the dry bulb thermometer because there is no water that is attached to the bulb of the thermometer. And then we're going to have what is known as a wet bulb thermometer. And here it is called a wet bulb thermometer because we have taken some water, we have soaked a cotton swab, and we have attached it to the bulb of the thermometer. So what should happen in this case is that we're going to take these two thermometers that we just looked at, and we're going to connect them back to back as such. So that means you have the wet bulb on the front side, and you have the dry bulb on the opposite side. From there, what we do is that we connect the two thermometers that you see here to a rotating rod. Now, for our case, the rotating rod I'm going to use is just the gray rod that you see here. And what I've done is that I've taken a simple screw and screwed it on the top, and the screw is going to go through the hole of the thermometers. So that means in this case, what that's going to apply is that now I have a mechanism to rotate this in the air. Now, in terms of the experiment that we're going to do, the best way to start this is to first take a look at the temperature in your dry thermometer compared to the wet bulb thermometer. Now, if you use room temperature water to soak your cotton ball, that means you should expect that the wet bulb and the dry bulb are going to have the same temperature initially. So for my experiment, for example, the temperature in this room is going to be approximately 74 degrees Fahrenheit. And that happens to be the temperature of the wet bulb as well. So now what we do is that we record this on a sheet of paper just for our record, that at the initial points, we have a temperature of 74 degrees Fahrenheit for the dry and the wet bulb. And now what we're going to do is that we just simply rotate this and spin it in the air, like such. And the idea is that we're going to spin this for approximately 30 seconds. Now the idea here is that as we spin this through the air is passing through the wet bulb and is going to cause the water that is within the cotton ball to evaporate. Now what we know is that evaporation is a process that tends to locally cool your environment. So that means as you begin to swing this around, evaporation is going to cool the wet bulb and it's going to keep the dry bulb temperature the same. So after 30 seconds, you can stop rotating and then you can take a look at the actual wet bulb temperature that is there. So for my system, it started at 74 and now the temperature reading is 70 degrees Fahrenheit. So after 30 seconds of spinning, I now have a temperature of 70 degrees Fahrenheit on the wet bulb thermometer. Now I do the same thing and repeat the same process. So I spin this again and again. And the goal is to see is that if I spin this for another 30 seconds, will the wet bulb temperature remain the same or will it continue to drop down a little bit? And so after you spin this for a period of time, you can then look at your wet bulb reading again. And in my case, the temperature has decreased from 70 degrees to 68 degrees Fahrenheit. So that means the temperature is still dropping, and that means I need to continue the process of swinging this in the air until it reaches a certain temperature. Now, as I continue to swing this back and forth, if there is no more water left to evaporate, that means the wet bulb temperature will remain exactly the same. However, if evaporation continues to occur, this will continue to cool down a good bit. So now after swinging that around a few more times, I have now gone down to 66 degrees Fahrenheit. And so that means I'm going to repeat the process again for another 20 or 30 seconds to see what my final result will be. Now, if I wanted to speed this up, I would just swing this faster and faster, but this is for the sake of demonstration. And now I stop. And what I see here is that my wet bulb temperature has remained the same. It is now 66 degrees Fahrenheit. So that means I've run out of water that can be evaporated. And now I have a distinct difference between the wet bulb temperature and what I'm calling the dry bulb temperature. Now, once you get that settled and once you are certain that you have evaporated all the water that you can, the next thing that you are going to have to do is to use those two values to determine what the relative humidity will be for your system. And that's the next step we're going to do in our experiment. Now, before we can connect the results of our experiment to relative humidity, we have to explain what relative humidity is as a variable. And the best way to understand it is to first start with the concept of temperature. For a gas, temperature is a measure of the average speed or motion of its air molecules. So when a temperature is low, the air speed is relatively slow, and as the temperature increases, the speed of the gas molecules tends to go up as a consequence. Now, relative humidity is not only a function of the moisture content in the atmosphere or the room. Relative humidity also depends upon the temperature of the air. So to explain this point, now to connect this to relative humidity, another variable that is often used is called the dew point. Now the dew point is the temperature that air would have to be in order for air to be saturated and for condensation to occur. The relative humidity is going to, in some sense, follow how the temperature and the dew point relate to one another. So notice that when the temperature and dew point get closer to each other, note that the relative humidity goes up. Now, when the temperature and the dew point are exactly the same, we say that the air is saturated, and therefore we have 100% relative humidity. As the air temperature goes up, notice that the relative humidity goes down. And that means that the air is further away from being saturated in terms of its temperature. So relative humidity is meant to give you a combined measurement of two things: the amount of water vapor or the moisture content within the air, but it's also meant to give you a sense of how close the air is to being saturated. And the main point here is to see that saturation occurs when the relative humidity is about 100%. So now with that being said, we can now connect this back to our original experiment. Now, once you figure out what the dry bulb temperature is and the wet bulb temperature is, you can use those two measurements to figure out what the relative humidity should be. So I'm going to use the values that were associated with my experiment. So initially, the wet bulb and the dry bulb started out at the same temperature of 74 degrees Fahrenheit. So that means we start with the column on the left and we find out where 74 is located right there. Now, after swinging the psychrometer in the air numerous times, one of the things I mentioned was that the wet bulb temperature went down to 66 degrees, given there. Now, what does that mean? When the wet bulb reached 66 degrees, that means the maximum amount of water was evaporated into the air around the wet bulb. And that means in the vicinity of that wet bulb, the air is saturated there. So that means the 66 degree Fahrenheit that you see there is essentially the same as the dew point temperature. Now the idea is that if you have the initial dry bulb temperature of 74 and you have the wet bulb temperature of 66, you can use those two values to find out what the relative humidity is. So once you are locating where the actual 66 value is, then you go to the top of your chart to see where does that intersect the relative humidity. And if you go up, you will see that intersects right there at 75%. So this means that if you have a 74 degree Fahrenheit dry bulb temperature and a 66 degree Fahrenheit wet bulb temperature, this correlates to a relative humidity of about 75%. Now, one of the things I want you to notice about this calculation is that it's meant to tell you something important. Notice that as the air temperature gets higher and higher, notice that more moisture needs to be evaporated into the air in order for this to be saturated. So for example, notice that at 74 degrees Fahrenheit, a 66 degree wet bulb temperature gives you 75% relative humidity. But if I were to increase the temperature to say 84 degrees Fahrenheit, in order for me to have the same exact relative humidity, I would need to have a wet bulb temperature of 75 degrees. So the point is, in order for you to get the same relative humidity, as you increase the temperature, the moisture content must grow with it to keep the relative humidity the same. So now we're going to look at the science behind why the sling psychrometer works. And so this is best explained by thinking about things that we do naturally. For example, let's suppose you wanted to dry your clothes outside. In what weather conditions would your clothes dry faster? In a hot, dry, windy day, or in a cool, cloudy day? You would basically say that you would dry your clothes in a hot, dry, windy day, and that tells you that you are expecting that it is easier to evaporate and get rid of water when you have hot, dry, and windy conditions that are prevalent. As another example, for those of you who blow dry your hair, why do you use a blow dryer to dry your hair? Now, the answer to that question is going to be the same as in the first image here. You blow dry your hair naturally because you expect that when you apply lots of wind and lots of air to your hair, you're going to remove a lot of moisture from it. That means you're expecting that evaporation should increase as you blow more and more air through your hair. Now, what is true for these two images is also true for the natural environment. Evaporation rates are high in hot, dry, and windy climates. That means we can talk about the basic factors which affect evaporation. And for our sake, there are 4 factors that matter. The first factor we're going to look at is temperature. Evaporation rates are higher at higher temperature for a basic reason. As the temperature increases, the amount of energy necessary for evaporation decreases. So that means in sunny, warm weather, the loss of water by evaporation is going to be greater than if you had a cloudy and cool weather day. Another factor that we haven't looked at is what is called the surface area. The surface area relates to how much of your object or how much of the water is exposed to the air. Now, what we expect is that evaporation should increase with an increase in that surface area. That's because if the surface area is increased, then the amounts of liquid that is exposed to the air is larger. And that means more molecules can escape from the liquid phase and go into the air in terms of vapor. So evaporation is greater when you have more of the water exposed to the air. That's why when you dry your clothes and you put clothes on a line, you stretch them out as far as possible because you're trying to make the surface area as large as possible. The third factor is the humidity of the air itself. Humidity, or the water vapor content of the air, also has an effect on evaporation, and this is connected back to our relative humidity arguments. The lower the relative humidity, the drier the air must be. And the drier the air is, the higher the evaporation rate must be. Now, conversely, the more humid the air is, the higher the relative humidity. And the higher the relative humidity, the closer the air is to being saturated. And therefore, there's less water that can be evaporated into the air. In this sense, this is why it is popularly said that warm air can hold a higher amount or a higher concentration of water vapor. So you can think of there being more room for water vapor to be stored in warmer air than for cooler air. So that's why if you were to dry your clothes outside, the best day is a day in which you know it's going to be hot and dry, so that you have high evaporation rates due to temperature and high evaporation rates due to low humidity. Now, finally, when it comes to the sling psychrometer, the last variable that matters is going to be wind speed. The speed at which air flows over the surface of water affects the rate at which the water evaporates. Here's the reason why. As the wind blows, it's going to sweep away airborne water molecules that are in the air. Now, the humidity of the air in the region in which this evaporation occurred is reduced, which allows more water molecules to get lifted from the water surface into the air. So that means the stronger the actual wind is, the greater the evaporation rate ought to be, because you are sweeping away water vapor molecules around the actual region, making the air drier, which therefore increases the rate of evaporation. Now, as we conclude this video, we can examine variations of this experiment that can be done either in the classroom or at home. So let's look at some common ways to cause variability in our actual experiments. The first is based upon the design of the sling psychrometer itself. As you saw in the experiment, you have to swing the object in the air, and that means the rate at which you swung depends basically upon yourself. Another way to perform this experiment is that instead of using your arm to spin the psychrometer, what you can do is that you can take your wet bulb and your dry bulb and then mount them to some object and then use a fan to evaporate the moisture in the air. Now, the reason that this is a good variation is because this will teach you how evaporation varies as the wind speed changes. It's much easier to control the speed of the fan than it is to control your hand as you swing it back and forth. So that means you can use a fan to estimate how quick it takes or how long it takes for the wet bulb to reach its steady wet bulb temperature. So that's one variation to repeat your experiment. The second variation is to perform this experiment in different regions or different locations. So for example, instead of doing this in a classroom, suppose you decide to do the sling psychrometer experiment after taking a shower, where the bathroom is going to have lots of moisture in the air. What you will probably see is that once you get out the shower, the relative humidity is going to be 90% or above. And so you can test that hypothesis by using a sling psychrometer as soon as a shower is done and there's still a lot of moisture in the air. Secondly, you can test your sling psychrometer whenever any weather system passes by. So how does the humidity change as a storm approaches and passes through your area? What you will likely find is that as a cold front passes through your area, you will see an increase in relative humidity as the front approaches you, and then you'll see a rapid decrease in humidity as the front moves away from you. Other examples would be, how would the relative humidity change while you're cooking in the kitchen, for example? Or how would the relative humidity change in nearby areas of your house? Do you think that your house has a steady moisture content, or do you think it varies? So all of these are ways that you can redo the sling psychrometer experiments and you can measure variations in the moisture content.